Hello, the title of the poster presentation is Conversion of Performance Model to Functional Model. The authors are myself H.G. Pavan Kumar, Sumail Singh Brar, Ashwani Aggarwal from Samsung Semiconductor India Research Bangalore, along with Seonil Choi and Wuju Space Kim from Samsung Electronics Korea. Coming to introduction, this poster describes methodology for converting cycle-accurate performance models to functional models intended for use cases like software development that demands faster simulation speeds. The main focus is to significantly reduce system C kernel synchronizations in the converted functional model without losing the functionality. Going forward, various behaviors of cycle-accurate model and methodologies to convert to functional model are described. Removing sensitivity on every edge of the clock. Typical cycle-accurate models will have processes sensitive on every edge of the clock, which will impact the simulation speed. Such processes should be identified and optimized. In this example, the performance model has consumer thread that is triggered on every passage of the clock, but the actual functionality is performed only when a particular register bit is set. In the converted functional model, the sensitivity is changed from clock to event, which is notified when the particular register bit is set. Removing blocking data structures. Data structures like SCFIFO, which are frequently used in performance model, become blocking when empty or full, thereby yielding control to the system C scheduler. Also, system C data types like SC int, SC unsigned int, etc. are not performance efficient. Hence, the converted functional model should use C++ data types. Converting child SC modules to C++ classes. Cycle-accurate performance models may have submodules with clear boundaries between them using the ports. To gain the performance, internal SC modules can be converted into C++ classes and set get APIs can be used to communicate between them. Conversion of processes to functions. Many processes of a module can be converted into C++ functions, which can then be called from top-level process of the module. Broadly, processes can be categorized into two types. A lossless thread is the one where the weights inside the thread can be safely removed without losing the functionality. By removing the weights, it becomes a C++ function which can be called from top-level thread of the module. A lossy thread is the one where there is at least one wait statement around which a state change is happening, which causes the other dependent methods or thread process to execute. In the below example, reg out can be thought of as the module state upon which other processes are dependent. When such a thread is converted into function, it is required to maintain the order of execution of interdependent processes. To achieve this, in the converted model, the thread is broken down into two functions, one having the piece of the code before the wait statement, referred as thread func waitX before, and the other having the piece of the code after the wait statement, referred as thread func waitX after. Now other processes sensitive on state change are executed after thread func waitX before. Later thread func waitX after is called. Combination of lossless and lossy threads. A module having multiple lossy and lossless threads can be converted into functional model with a single top-level thread calling multiple functions by maintaining a thread position variable. In the below example, mthread 0 underscore at is the thread position variable for lossy thread 0 that is controlling the order of execution of various pieces of the code of thread 0. Similarly, mthread 1 at is the state position variable for lossy thread 1. Now both the lossy thread 0 and lossy thread 1 are combined into a single top level thread along with some other lossy threads and lossless functions. Nested for loop example. A nested for loop having wait statement inside it can be optimized. In the below example, there is a wait statement inside the nested for loop labeled as x. There is another wait statement outside the for loop labeled as y. In the converted functional model, the nested for loop is split into two functions, funcx before, funcx after, to remove the wait statement labeled as x. As seen, the local variables I and j are changed to member variables m underscore I and m underscore j to retain their values between function calls. Also, the for loops are changed into if conditions but called the same number of times as that of the original model. To remove the white statement labeled as y, the converted model provides the function funcY after. Now the single top level thread of the module calls the functions funcx before, funcx after, and funcY after. The execution is controlled using a thread position variable and allows for other dependent functions that are sensitive on the wait statements. Sensitivity other than clock ports. Processes sensitive to ports other than clock ports will yield to system C kernel less often, but still they can be optimized. In the example, the cycle accurate model has two child modules, one waiting for the data written by the other. In the converted model, the functionality of the child modules are moved to the single top module and set function is used to update the port value required for the other thread function. Generic guidelines. Byte statement should not be put inside register handler functions because it can break the quantum of the core. Full or partial functionalities that are performance intensive should not be put inside the register handler function, but instead should be handled separately from an event notification. In case of IP containing TLM master, it should make use of DMA feature wherever possible, which provides significant performance improvements. TLM master should also use blocking transport interfaces since third-party IPs may not provide timing annotation for the non-blocking interfaces. If an IP is implementing a TLM master interface where data is more important than the address, that is, address is not relevant, then the burst of transfers in a cycle accurate model can be combined and sent as a single bit transport call. This completes the poster presentation. Refer the full paper available in the DVCon site, which has more details and code examples. The paper ID is 7017. Thank you.